Hello, everyone. Thank you for joining us for another live webinar session hosted by EE-Tech and All About Circuits. My name is Jeff Child, and I'll be your moderator. Today's session is brought to you by Vishay and is entitled Solutions Unleashed, Exploring Electronic Simulation with Nonlinear Resistors for Temperature Sensing and Circuit Protection. First, let me tell you a little bit about our two presenters today. Joshua Palema is a product marketing manager for nonlinear resistors portfolio at Vishay. He received his bachelor's degree in electrical engineering from the University of Nebraska and later received an MBA from Washington University. Josh began his career at the Boeing Company as a systems integration engineer, followed by a role as a test and evaluation engineer working on aerospace programs. He's been with Vishay for over 10 years and is responsible for product marketing in the Americas, supporting all the technical and commercial consumer opportunities for nonlinear resistor product lines. And then we have with us Alan Stoss, currently serves as product marketing manager for nonlinear resistors at Vishay. He's written several articles on electronic simulation and with thermistors and RTDs for Planet Analog. And he maintains a technical blog on Hackster.io that explores simulations using Vishay's components. Alan holds a Master of Science degree in Civil Engineering, Physics from ULB, and with a specialization in solid-state electronics and material sciences. So following this presentation, we're going to have a live Q&A session with Joshua and Alan, and you can submit your questions during this session using the chat box that you see up on the right-hand side of your screen. So please be on the lookout for a few poll questions that will pop up on your screen throughout the presentation as well. We're going to proceed now, so thank you so much for joining. And with that, I will hand it off to Joshua and Alan to get us started. Welcome.
Good morning, good afternoon, good evening to all those attending. Welcome to our highly anticipated webinar, Solutions Unleashed, Exploring Electronic Simulation with Nonlinear Resistors for Temperature Sensing and Circuit Protection. We are thrilled to have you all here as we embark on this journey of design excellence and innovation. My name is Joshua Palema, Vishay Product Marketing, and I will be kicking off this exciting session. I will be joined later by Alan Stoss, Vishay Product Marketing, with a special focus on design and simulation. Throughout the next hour, we will delve into a realm of possibilities where our comprehensive product portfolio, coupled with the transformative capabilities of electronic spice simulation, will empower you to reach new heights of design innovation. Our focus today is threefold. First, we will showcase our wide range of product solutions intended to revolutionize your designs. The product focus will touch on key features, functionality, and prospective application uses. Secondly, we'll share how our solutions can elevate your products to new heights of efficiency and performance through use of our advanced components and reference designs. This will be demonstrated through the exceptional capabilities of electronic simulation, enabling you to simulate and optimize circuit designs with unparalleled precision. With a special focus on nonlinear resistors, including NTC thermistors and RTDs for temperature sensing and compensation, as well as PTCs for inrush current limiting, we'll explore their significant role in various applications and highlight how they can be seamlessly integrated into your design. Lastly, we will open it up to the audience for any questions and comments. Without further ado, let's get started by exploring the product portfolio and how we can unlock the full potential of Vishay's nonlinear resistors through electronic spice simulation. Before we showcase our featured products, we must first define what product types fall under the classification of nonlinear resistors. Vishay's nonlinear resistors are passive components consisting of the following product classifications: thermistors, resistance temperature detectors, or RTDs, and varistors. The electronic symbol, component behavior, and typical use cases for each will now be outlined. Let's start with thermistors. Thermistors are thermal resistors based on ceramic or polymer technology, whose resistance varies significantly with temperature, meaning they are highly sensitive to temperature changes. Two types of thermistors exist: NTC, or negative temperature coefficient, defined by its beta value, meaning as temperature increases, the resistance decreases, and PTC, positive temperature coefficient, defined by its Curie temperature, meaning as temperature increases, resistance increases. NTCs are primarily used in inrush current limiting and temperature sensor applications, while PTCs are generally used as self-resetting overcurrent protectors, inrush current limiters, or self-regulating heaters. Thermistors are the most commonly used, cost-effective temperature sensors for many applications. Next are resistance temperature detectors, or RTDs. RTDs take advantage of thin film technology in which the element is a pure metal, generally platinum, nickel, or copper. The material has a predictable change in resistance as the temperature changes, which is defined by the temperature coefficient of resistance, or TCR. The TCR is positive in this case, meaning as temperature increases, resistance increases, as well as being nearly linear. As a result of its behavior, RTDs are widely used as sensors for temperature measurement and compensation functions across a wide temperature range. The last classification to discuss is varistors, or voltage-dependent resistors, VDRs. Varistors are electronic components with a current-to-voltage characteristic that is nonlinear. When triggered, the function of a varistor is to clamp the current created by excessive voltage. Varistors are often used to protect circuits against surge and undesirable transient voltages by diverting the excess energy away from the sensitive components. Vishay's nonlinear resistor product portfolio is comprised of a wide range of component options for design engineers to consider when temperature sensing, compensation, and electrical protection circuits are needed. The products outlined in this webinar show the depth and breadth of the nonlinear resistor product families from an electrical, thermal, and mechanical perspective. From wire-leaded through-hole to surface mount packages to housed assemblies, the options are limitless. It is also important to note that Vishay nonlinear resistors are well known for being design flexible, so in many cases they can be customized to fit a designer's unique requirements. I will now dive into more detail on Vishay's different product series within each of the classifications. It will be divided into two sections by functionality, starting with the temperature sensing products comprised of NTC thermistors and RTDs, followed by the circuit protection components, the PTC thermistors and varistors. First, I will discuss the NTCLE product family. This family encompasses all epoxy-coated NTCs with two lead wires, either insulated or non-insulated. They are commonly used in remote, typically in-air temperature sensing and control applications across all market segments. As is shown here, there are several different types to choose from, depending on your application requirements. A few critical features for many applications include temperature range, accuracy, response time, robustness, and qualifications, which are carefully considered in each of the product series specifications. The NTCLE 100 and NTCLE 400 series of parts are the standard commercial line and are the go-to for many consumer and industrial applications. The NTCLE 200 and NTCLE 300 series are part of the accuracy and automotive lines, with a key focus on high-end industrial and automotive applications, where long-term stability and robustness are required. Some of the specific product series will be put to the test during the simulation portion of this webinar, including the newest product to hit the market, the NTCLE 350. It boasts a peak temperature of plus 185 degrees C, while offering superior measurement accuracy through use of extremely low thermal conducting nickel iron lead wires. Next up, I will highlight the board mount NTC product families. The NTCS is a ceramic NTC SMD comprised of wraparound side terminations for soldering to rigid or flex PCBs. Conversely, the NTCC is a ceramic NTC die with top and bottom metallization layers for substrate mounting. The NTCS family of products are standard PCB mount components in 0402, 0603, and 0805 package sizes, and are used for onboard temperature sensing and compensation applications up to plus 150 degrees C. The NTCC family of products are silver terminated NTC die that are sinterable and wire bondable and rated for 175 degrees C operation. This product is geared towards semiconductor power module designs, think IGBT or MOSFET, where fast and accurate temperature sensing close to the junction is critical. The joining technology allows for a more tightly coupled thermal connection by sharing a common mounting approach to other power components within the module. Both NTCS and NTCC are available in a wide range of resistance and beta values with AEC-Q200 qualification, making them a viable option for many temperature sensing applications across all markets. Moving on to the NTCA family of products. The NTCA product family consists of what we call temperature sensor assemblies. Numerous product series exist within this family, and each is tailored to specific application requirements, with features such as fast response, high insulation voltage, thermal cycling withstanding, and reduced thermal gradient. In general, they are used for off-board temperature sensing with a convenient mounting method for system integration simplicity. Some of the standard housing types include lug, screw, and flex types for surface sensing, pipe and immersion types for fluid or ambient sensing, and plastic cap types for refrigeration sensing. These types are only the tip of the iceberg, as new customized housings are continually added to our product capability matrix. The NTCA family of temperature sensing components offer turnkey thermal management solutions for many end-use products in the market today. I will now shift the focus to the RTD resistance temperature detector family of products. Vishay has two available product series within this classification, the PTS and TFPT. Both are SMD components using precision-trimmed thin film technology on a ceramic substrate and come in sizes 0603, 0805, and 1206. The PTS uses platinum thin film while the TFPT uses nickel thin film. Both exhibit positive TCR, temperature coefficient of resistance, which is used to correlate resistance to temperature for sensing and compensation applications. This positive TCR provides a more secure failure mode behavior, since any potential positive resistance drift will generate a higher temperature reading, averting the system from thermal runaway. Additionally, RTDs offer superior stability of resistance in temperature, making for exceptionally accurate sensing over their lifetime. Due to their precision and stability, RTDs are commonly used in temperature measurement applications where reliability is key. Next, I will highlight a few product series from the PTC thermistor and varistor product families. The PTCE series are inrush current limiting or energy load dump thermistors, one in wire-leaded configuration, PTCEL, and the other in a surface mount configuration, PTCES. Two features that set these PTCs apart from other inrush current limiting techniques, such as NTC inrush or fixed resistors, are its ability to self-protect in case of overload, with no risk of overheating. PTCE can also absorb energy up to 240 joules and even higher when multiple components are used in combination. Operationally, the PTCE remains in a low resistance state, allowing ample current to still flow. When a short circuit or overcurrent condition occurs, the PTC will switch into its high resistance state, limiting the current flow in the circuit, or alternatively, the PTCE can be switched out with a relay when the system is stable. The PTCE products are heavily used in DC-link capacitor pre-charge or discharge circuits, among other applications requiring circuit protection. Two product series of varistors are also highlighted here. The VDR series of wire-leaded metal oxide varistors and the MLV series of multi-layer varistors. Varistors exhibit a nonlinear voltage to current relationship and function by providing high resistance under normal conditions and rapidly decreasing resistance when subjected to high voltage levels, making them very effective for surge protection and voltage regulation. Before we dive into how Vishay's nonlinear resistors can be simulated in your application, let's touch on some of the many applications across differing market segments where you are likely to find the products we've just discussed. Thermistors, as you'll recall, are temperature-sensitive resistors used for sensing, measurement, and control, as well as inrush current limiting functionality. Within the automotive market, applications consist of battery management and charging systems, power distribution, including inverters and converters, e-motor drives, pre-charge, discharge circuits, and thermal sensors for any number of vehicle subsystems. Similar applications can be found in the industrial segment. Additionally, robotics, HVAC systems, fire detection, metering, and test and measurement equipment are good fits within the industrial market. In the consumer market, thermistors are prevalent in domestic appliances, home automation, wearables, and lighting systems. Applications across alternative energy, medical, and military and aerospace markets are shown here as well. RTDs, as presented earlier, are highly accurate and stable sensors that are predominantly found in temperature measurement and compensation circuits of high reliability applications. Many of the application uses are found within the medical, aerospace and military, industrial, and automotive market segments. Some examples fall within the list of applications outlined here. Finally, varistors are voltage-dependent resistors that safeguard sensitive components in electrical circuits. Varistors are commonly found in all electronics with a power supply, with some examples being fabrication equipment, garage doors, medical systems, energy distribution networks, and domestic appliances. In summary, thermistors, RTDs, and varistors have diverse applications in various industries. Understanding their roles and choosing the right component is crucial for reliable system performance and safety. I will now turn it over to my friend and colleague Alain Stas, who will take you on a journey of innovation by showcasing the power of electronic splice simulation. More specifically, he will dive into some of the real-life applications we just highlighted, helping you to optimize your temperature sensing and protection circuit designs like never before.
Well, thank you, Josh. Now that we know all the nonlinear resistors product ranges from Vishay, it's time to work them out in applications. For design engineers, electronic simulation can be cost-effective and time-saving. That's why we are going to provide this reference book of simulation for Vishay nonlinear resistors. What is that? It's a digital file presenting our electronic models with plenty of links to the Vishay or partners' websites. Here you can see the different sections of the book for the through-holes NTCLE, the RTDs, the PTCL thermistors, etc., including VDRs and MLVs. The last section of the book leads to the summary of all available simulations with the corresponding software. Some of them are flagged with cups, whose number indicates the popularity numbers of views. We have used the following EDAs: Altium Designer, AltiSpice 17, MicroCap, Multisim, PSpice, PSpice 4TI, SaberRD, Symmetrix, and Tina TI. We have used as many software as possible for one good reason: to avoid problem of importing. Let's illustrate a typical problem of an import operation between EDAs. This simulation with a Vishay Opto device works in one software. We import it into another software, and what we get is a simulation abortion with plenty of error log nodes. Suppose that there would be a universal translation software which would understand the SPICE language. The translation of these error nodes would often be,
"I need some help. Can you correct all infringements to my own SPICE language?"
A good example of a plug-and-play model is shown now on the screen. A thermistor in the EDA Multisim from National Instruments. If this is your corporate software, just click on the link. You will be able to download the schematics on axter.io. A click on the downloaded simulation opens the software with this simple simulation of an NTC thermistor in a voltage divider. The NTC thermistor is here submitted to a temperature step, and the simulation results will be automatically provided. Now I duplicate a marker to show the external temperature. The markers are all ready. I calibrate my simulation from 0 to 30 seconds. And the results are there, showing the external temperature step and the NTC thermistor temperature and voltage variations. In fact, this is everything a designer needs because he will be able to integrate this in a future temperature control circuit. When you click on the symbol, you get the Vishay NTC thermistor netlist adapted in Multisim, and if you want to buy the component, there is a buy button on the Hackster website. Now we are going a little further in the complexity, and we are going to build an application based on a through-hole NTCLE 350 component. We would like to output and quantify a voltage from 0 to 10 volt for a temperature going from 50 degrees C to 185 degrees C? Well, here is the circuit where we can test our components in LTSpice 17 from analog devices. With not only the NTC tolerances R25 and B coefficient, but also the tolerances of all passive elements of the measuring bridge. This is in this case performed according to a Monte Carlo testing. The simulations are in fact very fast. Every sweep is done in a fraction of seconds. With some SPICE directives, we can then compute the measured temperature for a fixed output voltage, here 10 volts, and we measure a temperature going from 182 up to 185.5 degrees C. Let's simulate now the NTCC 200 or NTCC 201, the wire bondable bare die in an IGBT inverter application with thermal effects. Once again, we download the schematics, we open the circuit in LTSpice 17. This is a didactic inverter circuit with the full bridge of IGBT transistors, the gate driver ICs, the inductive load, the thermistor circuit which will drive the gate pulse modulation circuit. For this complex simulation, it's recommended to use the alternate solver. So let's verify that this is the case. Like always, is a plug-and-play simulation. We visualize here on the upper pane the power pulses dissipated by the IGBTs, and on the lower pane the temperature increase induced by this switching. On the lower pane, we visualize as well the pulse width modulated sinusoidal load current. The simulation is not that fast this time because of the high frequency switching. We see thus the continuously rising temperature, and this process needs to be derated when the temperature is too high. In order to do that, and that will be shown in the second simulation, we are going to reduce the switching duty time of the IGBTs. We see now that with this restricted switching duty time, the temperature remains stationary. The next example is a reproduction of a thermostat circuit which appeared for the first time in the book The Art of Electronics by Horowitz and Hill. This good old analog circuit is now completed with the oven of which the temperature must be controlled, and by the electrical and thermal modeling of the thermistor with its response time. The circuit works now in closed thermal loop because the room or oven temperature is fed back to the thermistor. We proceed to the simulation and we see that the oven temperature reaches the target temperature, 80 degrees C, then is properly stabilized by the heater current control. When we make a close-up of the oven temperature variation around the set temperature, we can see the proportional control performed by the circuit. We can also proceed to change in the target temperature setting and ask to the system to stabilize at different levels. For example, 40, 60 or 80 degrees C. The heater current controls will be made accordingly. The NTC thermistors are very sensitive to self-heating, and it is possible in LTSpice 17 to measure the dissipated power by pointing a device and press on Alt key. This power is then drawn onto the screen. We measure a power going from 2 to 5 milliwatt, which is a bit too high for a value of 2.2 milliwatt per Kelvin for an NTC LE203. We can reduce the self-heating by increasing the resistance value of the thermistors and the fixed serial resistor from 10 kiloohms to 100 kiloohms. For the thermistor, we can directly change the sub-circuit name from NTCLE 203E3103 to 104. Performing again the simulation with the new components, we see that the power is strongly reduced. Let's introduce now the tolerances on the thermistor characteristics R25 and B value. Not forgetting that the tolerance on the B value has changed because we changed the 10 kΩ by 100 kΩ. Let's do the worst case analysis, and before we see the result, let me point out the speed of the simulation. We see here how close we are from the required set temperature. The last characteristic that we are going to sweep in this simulation is the response time of the thermistor, for example, in function of its housing. We can test value from 7 up to 60 seconds. The result shows then the overshoot corresponding to all these response time values. Another successful type of simulation concerned the fire detector application. Thus, it was worthwhile to dedicate a part of this webinar to these useful devices. Here is a siren buzzer circuit based on a cascade of two 555 timers. Some words about the circuit behavior before we do the simulation. When the temperature is normal, Q1 is conducting, and the SW node voltage is kept low. As temperature increases, the NTC resistance will decrease, the voltage at the NTC node decreases, and at a point Q1 is blocked. The 555 timer U1 is reset. Vout gives a pulse signal, which will reset the second timer to produce a new pulse at another frequency. That's the siren noise. In fact, LTSPI 17 allows to save voltage as some files, so we can hear it now during the video. So let's go for a simulation. We set the fire alarm circuit on with the start switch. We apply the temperature step, and watch your ears now. It's over. Hopefully it was a false alarm. You see and hear that the noise stops when the NTC temperature goes back to a normal value. If we want the noise of the fire detector to stop only when the power supply is switched off, we can add this SCR to the circuit. So in this case, even if the thermistor goes back to normal temperature, the siren noise will go on until we switch off the power supply. So let's go for a second noisy experience. The detector is switched on. The temperature is going to increase now. So we see effectively that the alarm stops only when we switch off on the power supply, long after the thermistor is back to ambient. This brings more security to the heat detection for the case where the thermistor would go into open circuit after alarm has started. A manual switch off of the siren is in this case necessary. So enough for today of this annoying siren buzzer noise. So we can go back to a simple detector with one 555 timer. Yet, with another new feature. The circuit is a rate of rise detector. It will work with the speed of increase of temperature rather than with a fixed level. It contains two NTC thermistors. One exposed which reacts quickly and another protected with slower reaction. If the temperature variation is really slow, like for a natural variation of ambient, even rising up to 50 degrees C, the switch will not happen, as the voltage VB will remain constant. At the contrary, if the variation is faster than a predefined threshold, the exposed thermistor value will decrease before the other, VB will reach the required low level, and the detector will switch on. Let's confirm all these provisions with a simulation where we apply temperature gradients which are going to be slower and slower. We will see then when the detector will not switch anymore. Let's look at the result of the first simulation. We see how the two NTCs reacted differently in speed to the gradient, and that the detector switched when temperature has reached 50 degrees C after 110 seconds. We see here that the switch happening at 12 degrees C per minute does not operate at 6 degrees C per minute, even if the final temperature is the same around 50 degrees C. When we plot all the results in function of the gradient intensity, we conclude that the detector does not switch with a gradient under 6 degrees C per minute and switches 100% for a gradient above 7.5 degrees C per minute, which is in fact the goal of this type of detector. Now we are going to show an example of application for the PTS, the platinum thin film SMD components. They will be used here as elements of temperature compensation of active elements in a logarithmic amplifier. This kind of device can still be found in some instrumentation applications in signal compression or conditioning. I found this circuit first in the book The Art of Electronics, but it appears as well in a tutorial of Texas Instruments on high-speed log amplifiers. The outputs Vout of these two circuits are proportional to the log of the input voltage Vin. The only difference between these two circuits is the compensation in the one of the upper pane with the presence of a PTS 1206 1 kΩ, which has a positive temperature coefficient of about 0.4% per Kelvin. In the provided simulation, AltiSPy 17 computes the output voltages in function of the Neperian logarithm of the input voltages with a supplementary temperature sweep. And we see as a result the obvious temperature compensation with the blue curve compared to the uncompensated one in green. As already said, we strive to have a multi-software approach of the simulation. The following is a schematics of a piezoelectric strain gauge recreated in AltiSPy 17 first, under a form of a variable resistor changing in a linear way with the strain, which is applied under the form of a voltage V strain with the equivalence 1 microvolts equals 1 microstrain. Sweeping the strain from -5 mV to +5 mV, we plot the current through the gauge and see its strong temperature dependence. To reduce this temperature dependence, we place the strain gauges into a Wheatstone bridge and we tune the voltage applied to the bridge via a fixed resistor thermistor network. We will thus apply this technique directly onto a circuit with 4 strain gauges placed in the Wheatstone bridge, which compensates partly the temperature dependence. As the temperature will increase, the resistance of the NTC decreases, increasing the bias voltage onto the bridge. For a fixed strain, we will sweep the temperature and compute the bridge voltage for an compensated bridge on the left and for an uncompensated bridge on the right. We set up a linear sweep between the limit temperatures, and here is the simulation result with the green stabilized curve against the non-compensated one in blue. The strain voltage is now swept with a variable temperature, and we see how the noise in temperature is globally reduced. The same schematic has been reproduced in other electronic simulation software, for example here, Symmetrix from Symmetrix Technologies. Importation processes of the strain gauge model and the thermistor model have been performed. The provided simulation will work as plug and play. Multisim from National Instruments is next. In Multisim, the component wizard is used to import the different models. The same simulation results in Multisim come as no surprise. The same is applicable to PSpice from Cadence. In general, all these software have some particular syntax points which could induce a simulation bug. Nothing like that will happen here because all importation processes have been completed successfully. The simulation result is once again confirmed by PSpice. Next, we come back to the popular simulations and to transient temperature sensing. A Vishay-leaded NTC model will be included in a closed loop of a PID temperature control circuit with a thermoelectric Peltier element. Peltiers are very popular in mini fridge devices, in optoelectronics, laser diodes, industrial electronics and telecommunication, and also in mini incubators, IT enclosures, and more. The heat removed from the thermal mass by the Peltier induces a temperature drop which is fed back to an NTC thermistor in a Wheatstone bridge, which compares the NTC resistance to a set profile. The bridge voltage is then used by a PID controller to tune the Peltier current for closed-loop temperature control. Once again, it's a plug-and-play simulation. Just press on Run, and different waveforms are directly displayed on the screen. On the lower pane, the cold thermal mass temperature, the set temperature, as well as the ambient temperature. On the upper pane, the offset between this thermal mass temperature and the set temperature. This represents, in fact, how precisely we control the temperature. And on the mid pane, the Peltier current needed to achieve this control. It's also a worst-case analysis. All the extreme values of the thermistor parameters are taken into account, but also the other fixed resistor parameters in the bridge. At the end of the simulation, we can see that the temperature control remains within plus or minus 1.2 degrees C. Let's leave SPICE simulation for some moments and let's go to the cloud in order to simulate our components in the web tool Part Quest Explorer. This is a pre-charged circuit simulation where a network of PTCs must allow to load a smooth capacitor and eventually switch to blocking state in case of overload. We will come back to such circuit in the last part of this webinar. For the moment, I would like to point out that all the Vishay thermistors and RTDs are in the partners library of Part Quest Explorer, with links to officially approved disties. Almost the same pre-charged circuit for electric vehicles can be launched in LTSpice 17. We will use here the 120 ohms of the series PTCl17. We begin to know the drill on how to download the schematics. We have here the classical pre-charged circuit with a tri-phase voltage source, a smoothing capacitor and a load, a PTC network containing 4 PTCl, plus some electronics which will cut off the PTC network after charging and which puts then the current onto the load. The goal of this simulation is to test 4 rising values for the capacitor and to see if the capacity can be charged without PTC switching. This is done for an ambient temperature of 50 degrees C. We start the simulation and see if in these conditions the charging happens flawlessly. Once the capacitor voltage has reached a defined value, the current is switched onto the load within a requested timing. We have tested 4 capacitors values and we have 4 disconnections. Then suppose that you realize that the maximum ambient temperature can be 90 instead of 50 degrees C. This requires a new simulation. We change the value of this ambient temperature in the SPICE directives and we rerun the design. The 3 first values pose no problem, but at the 4th one, the temperature of some of the PTC is becoming relatively high, some of the PTCl begin to switch, and the required capacitor voltage level won't be reached. There will be no disconnection within the delay of here 1.5 seconds. Our design is only partially successful. So what can we do? One possibility is to increase the total thermal mass of the PTC network by adding 2 more PTCl in parallel. We connect properly the new designed network. We take the opportunity of this design change to add a common connection inside the PTC network in order to equilibrate the different branches. We rerun the simulation, and of course there won't be any problem for the 3 first values of capacitance, but what will happen for the 4th one? The charging seems a little bit hard, but yes, we did it. The disconnection has now happened for the 4th values, and our design is now completed in the most severe conditions of ambient temperature. Remains now to order 4, possibly 6 PTCEL, to build the circuitry in the real world and to verify that the predictions were right. We approach the end of this webinar about the simulations of Vishay thermistors and RTDs. Not forgetting the VDRs and MLVs, for which we supply simulation when you can learn how to clamp over voltages or realize some special designs. Well, this webinar is now over. I hope that you have received a good overview of the content of the Vishay book of simulation for nonlinear resistors, and it is time for me now to ask you my question of the day. Do you wish to receive a copy of this simulation kit book for Vishay nonlinear resistors? Thank you very much.
Joshua and Alan, thank you for that great presentation. I know I personally learned quite a bit, lots of good hands-on information there. We already have several good questions from the audience, but we always want more. So if there's any more that you want to jump in and put in the chat box, please do. So with that in mind, Alan, Josh, are you ready to answer some questions?
Yeah, for sure.
Okay, the first one is, if I create a simulation with Vishay models and I run into problems, is there an email address I can use to contact Vishay to get some help?
Josh, do you want to answer?
Yep, I'll take that one. Thanks a lot. So yes, just for this specific question, we have a dedicated email address for these types of questions. So that email address is edesign.ntc@vishay.com. So just one thing to keep in mind, always be sure to join the simulation file. And as Alan mentioned during the webinar, we have the ability to support, several of the most commonly used design software. So again, that's edesign.ntc@vishay.com.
Yeah.
Excellent. That's great.
Yeah, and if the request is joined by a simulation in LTSpice, for example, there will be no problem. We might not have all the licenses for all this software because it costs a lot of money. But if it is LTSpice or PSpice for TI, there is absolutely no problem. We will try to solve the questions.
Excellent. And I'm just going to repeat that. It's edesign.ntc@vishay.com. So
Correct.
Next question. Is there a plan to explore new software other than the ones that were talked about here today?
Yes, we have a plan to present simulation results of NLR component in Simulink Simscape from the MathWorks. In fact, there are already results available with NTC thermistors and RTDs in MATLAB Central. So that would need a follow-up of this webinar. So we are working also on models for PTCEL in
I think you might have dropped off there for a second, but yeah, I'm just going to continue on to the next question. If someone's using components from Vishay other than nonlinear resistors, and you can't get models for it, what can you do?
Okay, yeah, I can take this one. So, yeah, very similar to the edesign.ntc. So, Vishay has a broad selection of semiconductors and passive components. Generally speaking, for I would say the active components, there's a lot of SPICE models available out there in the web. For the passive components, we'll do our best from the thermistor side to support our colleagues that have other passive components. So in the event that you're unable to find a specific model or you have a question about a model that you're creating, the best thing to do is really going to be to submit the request to the @vishay.email address that is residing within this specific product data sheet that you're interested in. So again, each data sheet has a dedicated email address for that specific product. So that's the best place to start with any questions that you might have for products other than the Vishay nonlinear resistors.
That's excellent. Back in the old days, it used to be phone numbers, but now you can just email. That's awesome. Yeah.
Yep, perfect.
Next question. All the simulators which were exposed are typical using analog electronics, but what about things like digital temperature control? Can you talk about that a little bit?
Yeah, I'm sorry. I was.
Yeah, welcome back. Yeah, there's a little technical difficulties.
I was disconnected. Yeah, in fact, all the simulations that we presented were analog. But, and you know that the world is presently digital. But our models can be used, for example, in the web tool PartQuest Explorer, which is a multi-domain simulation, cloud-based simulation tool. And there you can design your digital application with a component. I given the reference in the simulation kitbook. Also, models are provided for TINA TI, and there is a soft design TINA Cloud, which is also using VHDL-AMS simulation language. So I guess that models can be used in digital simulation in this tool. But the real treat has been given by a company named Corvor in 2023. There is a new SPICE program, which is called QSPICE, which has been developed by Mike Engelhardt, who is at the origin of LT SPICE. So he has just developed a new SPICE program, which is supporting Verilog and C++. So this is some kind of futuristic SPICE program. And of course, we already made some models compatible with this program. So if there is a follow-up to the webinar, we will be able to show the function of NLR component in a new QSPICE program with also possibly Verilog modules. There are already some simulation of the digital temperature controller available on Axtor.io. And if there is a follow-up to this webinar, we will certainly show plenty of simulation of digital temperature control.
Excellent. Yeah, I've heard about QSPICE. That's pretty popular. Interesting.
Yep.
Yeah.
It's becoming very popular. So it's as efficient as LT SPICE. And as I told, it's compatible with Verilog and C++. So that's the SPICE of the future. Yeah. And we want to jump in the bandwagon.
Yeah, of course, yeah. You also mentioned cloud-based tools. I think those are becoming very popular these days, especially for younger engineers.
Yep.
Another question, Vishay is exposed to lots of simulations. I guess as any engineers, they want to know, are these results accurate? So how can we be sure that the simulated results are correct?
Yeah. So just like for any, in any electronic simulations, the quality of the result is always linked to the quality of the models, which means if you put garbage in, there will be garbage out.
Right.
And we, as a component manufacturer, we have tried to implement as precise models as possible, including all the characteristics of the NTC thermistor, for example, the strain out and out coefficient, the self-heating, the tolerances of the component, as well for the PTC. We have simulated VDR effects and tolerances, and so we, as a component manufacturer, we are owner of our characteristics. So all these characteristics have been included into the models, and this way we really hope that we will give predictive results. And by the way, we have never had any complaint of any customer about contradictive results, especially for the PTC, for example.
That's a good track record. Okay, it looks like that's all the questions that we have come in so far. We're going to just wait a couple minutes for some to come in. And while we wait, Joshua and Alan, is there any sort of other takeaways or elaborations you want to mention for the audience while we wait?
Yeah, Josh, do you want to answer to that, or?
Yeah, I guess from the just one comment that it was highlighted on the initial part. So from the product perspective as well, we have just to keep in mind that a lot of the products you see here are going to be catalog type of products, but we do offer a lot of custom solutions, whether that be from an electrical standpoint, a mechanical standpoint, thermal standpoint. So just again, if you're not finding what you're looking for, feel free to reach out to us at Vishay, and we'll do our best to support with some of that customization and solutions that are meeting your needs.
And there is a simulation, the electronic simulation, and there are toolkits. So this will be sent to all the attendants of the webinar. In there, you will have the links to all the simulation that we have done up to now, including the new ones on the QSpice, because each time we have new additions to this simulation toolkit. So that's what we want. That's what we want to give away to all the people, and are hoping that it will help to develop good application circuits for their applications.
That toolkit sounds very interesting, and Joshua, the idea of customizing things at this level of component, that's very interesting. I think that's any engineer has to keep those things in mind. Okay, well, it looks like that's it for the questions. And so Joshua and Alan, I want to thank you for an excellent presentation, and it was a great Q&A discussion. Everyone, just in a moment, you're going to be redirected to Vishay's hub page on All About Circuits, and there you're going to be able to view this session on demand anytime you want, and then you can also view other Vishay webinars and resources that are available there. So thank you all for your time, and we look forward to seeing you again in other live sessions. Thank you. Have a good day.
All right,
thank you very much.